Okay, so the plan for today is to finish up section 8.1. It's a little bit of a big section, so it might take us a few more minutes to actually finish up that one section and then move into sections 8.2 and 8.3. Uh, so we're working with radicals, radical expressions, roots, um, and rational exponents. So that's kind of our goal for today is to make it at least get a good start on 8.3. Uh, Two quotes of the day today. They're both chess quotes, but I think they apply more broadly to life. The first is by the second world chess champion, Emmanuel Lasker. When you see a good move, look for a better one. And the second is by current Grandmaster Maurice Ashley. There are three types of trades: forced, fantastic, and foolish. If it's not forced or fantastic, it's foolish. So in chess, when you make a trade of pieces, like if you say capture your opponent's bishop with your knight, and you're expecting them to recapture your knight, that would be making a trade, and that's a type of move that fundamentally alters the game from that point forward. I no longer have, I forget what I said, but I no longer have a knight, let's say, and they no longer have a bishop. That changes the game for the rest of the game. And I think, great chess quotes in general, good advice in general. But I think also, when applying to life, I think Maurice Ashley's quote kind of is basically saying if you're uh, the bigger the decision you're making or the more impact that it's likely to have, maybe the more care should be taken in making that decision. Sometimes you're just forced into a decision and that's the way that it is. Um, but try to avoid, making huge decisions rashly because, the result might be either fantastic or foolish, right? It could be kind of extreme either direction. Um, and when you see, what seems to be a good decision, don't just stop there. Ask, is there something better out there? Right? Maybe this is, you graduate, you're looking for a job, you get a couple job offers. Is there a different direction you could go other than just the offers that you were given? Um, and when you're deciding to make, when you're deciding to accept one of the job offers, which one should you accept, right? There might be one that has a little more risk, but gives a little more reward versus another one that's a little bit more of a kind of a sure thing, but a little bit less upside. So those kind of decisions, they're the kind of decisions that are tough to make and that maybe the deserve the uh, amount of effort and cognition that, that's in line with the impact that they could have. But that being said, if you're going to make a foolish decision or if you're going to make a risky decision that might pay off big time or might flop, when you're young is the time to do it, right? When you don't have, family and kids and all of that depending on you, and when you have time to kind of dig yourself out of it, if things go a little bit wrong. So, all right. So moving on to 8.1, we already worked through a couple of problems, these two problems last time, but I'm just going to go back through them just to kind of rehash the ideas a little bit and give us a little bit of momentum into the next couple of problems. So I won't be going back through all of the details, but recall that when we write the radical sign like this, so we have radical 25/64, this is the principal square root, this is the positive square root. So the square root of 25/64, we know that there's going to be a positive square root, but also a negative square root, because if I take negative times negative, that gives me a positive output. And I note that 25/64, I could write as 5/8 squared like this, and I could square root that. And basically the square root symbol, in some sense, undoes the square operation. And this gives me 5/8. So we say that the square root of 25/64 equals 5/8 because 5/8 squared equals 25/64. But note also that negative 5/8 equals, or negative 5/8 squared equals 25/64 as well. So this is what we call the principal square root. So radical 25 over 64 is really the principal square root, but pretty regularly we just call it the square root, recognizing the fact that there is a negative square root as well. If I have a question like this one that I want to simplify, negative square root of 0.01, or this would be negative square root of 1 over 100. Well, 1 over 100 is 1/10 squared. So this is negative 1/10. This is perfectly okay to do, right? Square root of 0.01 is 1/10 because 1/10 squared gives me 1/100th or 0.01. And this negative sign just comes along for the ride. Note the difference between this question and a question like, say, square root of negative 0.01, where the negative sign is on the inside of the square root. Well, here, not really sure what to do. Should this be like, 1/10? Well, 1/10 squared gives me positive 0.01, not negative 0.01. Well, maybe it should be negative 1/10. But negative 1/10 squared also gives me positive 0.01, not negative 0.01. So there is no real number that this simplifies to. A little bit later in the course, we will look into complex numbers, but for right now, we're sticking with real numbers. So at this point, we basically say, well, this just doesn't make a whole lot of sense to us right now. There's really not much we can do with this. Again, later on in the course, that will change a bit, but for the time being, square root of negative number, just it kind of doesn't make sense. Now, what about something like this? The fourth root of 256. If I could write this as, switch back to normal color. If I could write this as the fourth root of something to the fourth, OneNote loves correcting my 4s to 9s, and I don't know why I picked so many problems that have 4s in them. It seems like every other problem has a bunch of 4s, but it's probably just confirmation bias because when I have 4s in a problem, I notice it. If I could write this question, if I could rephrase it as the fourth root of something to the fourth power, then similar to the square root, the fourth root just kind of gets rid of the fourth power, right? We have a similar idea that the the fourth root of a number equals another number. Let's say implies m equals n to the fourth. So the fourth root of m equals n if it's true that n to the fourth equals m. We write the fourth root as like the square root sign with this little 4 inside of that little piece right there. Okay, so 256, I would like to write it as something to the fourth. Well, I know that I might recognize it as a power of 2, but if I don't, I know that I can factor out a 2. So I can have 128 times 2. 128 has, well, even a factor of 4 in it. I can see that pretty easily. That's 120 plus 8, or 32 times 4. Or this is 2 to the 5th times 2 squared times 2 to the 1st. Or I actually recognize this as 2 to the 8th power. And using some power rules, 2 to the 8th power is 2 squared to the 4th power. Or 256 is 4 to the 4th. So if I take my number that's under the radical sign, if I get its prime factorization, that helps me break apart what all is going on here and split it up into the fourth power of something. So I have lots and lots of 4s in this problem. So it's the fourth root of 4 to the 4th power, or that just ends up being 4. Again, this is something like the principal fourth root. 4 to the fourth power equals 256, but also negative 4 to the fourth power would be 256 as well. So negative 4 would be another fourth root of 256, but it wouldn't be the principal fourth root. So if we write, fourth radical 256, or if we say something like the fourth root of 256, we're implying the principal fourth root. So any even root, like the square root or the fourth root or the sixth root, is going to have this this idea where there are two roots, because if I took a negative number to an even power, the negative gets squared off and becomes positive. But when we write this symbol, we mean the principal root, the positive one of those. And similarly, as up above, asking a question like, what is the fourth root of negative 256? Again, this just doesn't make sense to us at this point. Because if I take a negative number, say like negative 4 to the fourth power, that negative squares off and I get positive 256. And if I take 4 to the fourth, I also get 256. I don't know how to raise something to the fourth power and get a negative number out. So again, this doesn't work too nicely, not a real number. Now, on the other hand, this might also, initially lead us to say, oh, I think this is not a real number, the cube root of negative 8. But for the cube root of negative 8, so the cube root of m equals n implies that m equals n cubed. Am I able to cube a real number and get a negative number out? Yeah, I actually am. So for an odd power, for a cube or for a fifth power or a seventh power, if I have negative number to that power, the negative number sticks around, right? So for instance, negative 3 cubed equals negative 27, but 3 cubed equals positive 27. So I actually can, in some sense, like tell apart my, number one, my two different roots, plus or minus 3, they correspond to two different results, right? So negative 3 cubed is negative 27, and positive 3 cubed is positive 27. So number one, we don't have this business with a principal root, where each one of these is just going to have a single root. And number two, I don't have this, you might call it something like a domain restriction. I don't have this restriction that I kind of can't use a negative under the radical sign. That only applies to even roots, square roots, fourth roots, sixth roots. That's where having a negative sign under the radical doesn't make a lot of sense, because when I rewrite the other side of the definition, that even power squares off the negative and I get a positive output. But an odd power allows that negative to just pass right through, and we can get a negative output from an odd power, from a cube or from a fifth power or something like that. So the cube root of negative 8 is actually negative 2, because 8 is 2 cubed, and negative 8 then is negative 2 all cubed. So this is a perfectly fine radical for us to evaluate here. The cube root of negative 8, perfectly fine. The sixth root of negative 64, again, here we would say not a real number. we might recognize that 2 to the 6th equals 64. So it kind of like almost works out, or it feels like it might work out. But negative 2 to the 6th, be really careful with your parentheses here. Is that like negative 64? Well, no, the negative squares off and makes a positive 64 as well. So what can I plug in, raise to the 6th power, and get a negative 64? Well, if anything does satisfy, this is certainly not going to be a real number. If I take the 6th power of a negative number, it's going to be positive. Of a positive number, it's going to be positive. And of 0, it's going to be 0. None of those yield a negative output. So here we would just say, not a real number. At least at this point in the course, this doesn't make sense to us. We really can't make heads or tails of what's supposed to be going on here, right? At this point, this is a collection of symbols that just doesn't make a lot of mathematical sense to us, right? We could write down lots of mathematical sentences or statements that just are completely meaningless in terms of the symbols they use. So the same way that you could take a whole bunch of English words and, if you pick the first 10 words that you randomly found in the dictionary and put them one after the other, it would make a meaningless sentence. Each of the words makes sense, but the meaning, it doesn't have any grammatical meaning or any real meaning. Same thing here, like a negative sign or a 64, a radical sign, a sixth root, they all make sense, but putting them together in this way, at least at this time, doesn't make sense. So we just say something like not a real number or, does not exist or something like that. We probably don't want to say does not exist because a little bit later in this course, we are going to be introducing complex numbers, which do deal with this kind of an issue. Okay, and then last example in this section. So consider the square root of 17. We would like to, one, figure out which two integers it's between, or in some sense, approximate it to a single digit of accuracy. Oh, and then that should be 17. I started with square root of 68 and figured that was just the calculations were a little too tedious. So, and then we'll approximate square root of 17 to one decimal place without using a calculator. Okay, so I have that square root of 17 equals some number n, says that n squared equals 17. Well, one thing that I realize is that the squared function, n squared, this is an increasing function for the positive inputs. If I put in a larger positive input into n squared, I get out a larger positive output. So if I can find a positive input into n squared that gives me an output that's less than 17, and if I can find another positive input that gives me an output that's greater than 17, then I'll know that the positive input that gives me exactly 17 out is going to be between those two numbers. This makes use of something a little more formal called the intermediate value theorem, which we aren't really discussing in this course, but this is all whatever kind of set on very firm mathematical foundations, not just my hand wavy explanations. So n squared equals 17. Well, I know that 4 squared equals 16, and I know that 5 squared equals 25. So I know that n has to be between 4 and 5. Or n has to be 4 point something. So if I had to place square root of 17 between two integers, square root of 17 is between 4 and 5, or square root of 17 equals 4 point something. So we got kind of our integer place down. We figured out that it's got to be 4 point something. Can we get another decimal place of accuracy? Well, how did I do this? I basically picked some integers. I checked that 4 as an input gave me a smaller output than 17, and 5 as an input gave me a larger output than 17. And then I was able to stick my square root of 17 between 4 and 5, between two consecutive integers. I probably should have said between which two consecutive integers. We could say it's between like 0 and 4 billion or something and be done. But we're looking for between two consecutive integers. So what does approximating it to one decimal place look like? Well, it's the same strategy. There are slicker ways to do this, but we can do a trial and error. We know that 17 seems to be quite a bit closer to 16 than it is to 25. So I think it's going to be 4 point something where the something's going to be kind of small. It's not going to be like 4.9. It's going to be like 4.1, 4.2, something like that. So let me try 4.1 squared. So I get 41 and 4 and 16. Make sure I did that right. Looks good. I have one decimal place here, one there. I have two in the answer. So 16.81. And this is less than 17. So 4.1 is below square root of 17. What's 4.2 squared? If 4.2 squared is also below 17, then I'll go up to 4.3 squared, and I'll keep going until I get a consecutive tenths place where I have one input gives an output below 17, the other gives an output above 17. So if I multiply these two together, I get 17.64. That is bigger than 17. And I see that square root of 17 then is between, so square root of 17 squared equals 17. Square root of 17 is between 4.1 and 4.2. Or square root of 17 equals 4.1 something. So to one decimal place of accuracy, it is 4.1. And then I don't know what the second decimal place is. I don't know what the hundredths place is, but I know the tenths place is 1. Now, there are many slicker ways to computer estimate square roots, going all the way back to even the Greeks had, the ancient Greeks. Of course, the Greeks today have good ways to estimate square roots, but the ancient Greeks, pre-U zero, pre-year zero, had good ways to approximate square roots and things like that. So, this is a very old problem, but just using the definition, we can get an approximation. Not the most efficient way, but it is a pretty simple way, and it's a pretty, it's a very direct application of the definition. Are there any questions on 8.1? Okay. Okay, so moving on to 8.2 now. Now we're going to start looking at, and I'm blurring the lines here. I think the book handles a little bit of this variable stuff in 8.1 and some more of it in 8.2. So I just pushed all the variable stuff to our consideration of 8.2. So now we're looking at simplifying radical expressions, but where we have a variable in it. So instead of simplifying roots that, just kind of radical of number, we're now looking at how we handle expressions like this with variables in them. So I have a little bit of a nuance here that I need to respect, and that really throws a monkey wrench into a lot of these problems. I really kind of want to write square root of x squared equals x, or cube root of x cubed equals x. It seems like the square root kind of undoes the square, or the cube root undoes the cube, and that's kind of correct. But let's kind of check. If I were to look at the cube root bit down here, I see that if I put in, say, x equals 2, then the cube root of 2 cubed is the cube root of 8, which is 2, and that doesn't make sense because 2 cubed equals 8. Or if I put in x equals, I don't know, -1, cube root of -1 cubed is the cube root of -1 is -1 because -1 cubed is -1. So if I put in a value for x, I get that value out. Let's check the one up here. If I plug in, say, x equals 2, the square root of 2 squared is the square root of 4. The principal square root of 4, of course, is 2. That looks good. If I plug in 2, I get out 2. What if I plug in -2? Does this just blow up? Does this just not work? What happens? Well, square root of -2 squared is, well, -2 squared is +4, is the square root of 4, but the square root of 4 under the radical is 2. So wait, I plug in -2 and I get out +2. Or I plug in +2 and I get out +2. I get the same magnitude out that I put in, but the sign is always positive. Well, I have an operation that says to do that. It says, give me back the same magnitude as the input, but always make it positive. If the input's negative, make it positive and yield that as the answer. If the input's positive, leave it alone and give that as the answer. This is actually the absolute value of x. So the nth root of x to the n, well, if n is even, like a square root of x squared or a fourth root of x to the fourth, this yields absolute value of x. If n is odd, well, the odd root of the odd power, the negative sign just, in a sense, kind of passes through all of that. And nothing gets rid of the negative sign. And so we hold on to the negative sign. We don't make any change. So this is actually an important nuance. So we'll have to be careful when we do simplifications, like, say, the 6th root of x to the 6th. We don't want to just write equals x. That's kind of pretty close to right, but really it's absolute value of x. Okay, so what about something like the cube root of m to the 9th power? So here I want to rewrite m to the 9th as something cubed. I know my power to a power rule, x to the a to the b power is x to the a times b. So if I want m to the, say, k power, I need 3 times k equals 9, or m cubed to the 3rd power. This would be like m cubed times m cubed times m cubed. There's a total of 9 factors of m there. That looks good. So this is the cube root of something cubed, particularly m cubed. Remember, with an odd root of an odd power, we just get the original thing back. No need for square roots here. So this is just going to be m cubed. And that's our answer. Now, if I look at something like the 4th root of x to the 12th, I want to write x to the 12th as something to the fourth power. Well, x to the 12th is x cubed to the fourth power. So here I have the fourth root of something to the fourth power. This is going to give me that thing, x cubed in this case. But now I have to be careful. I took an even root of an even power. So I do need to throw absolute value signs on here. If I were to look at the next one, fourth root of x to the 16th, I can do something similar. X to the 16th is what to the fourth power? It is x to the fourth to the fourth power. Or this is the fourth root of x to the fourth raised to the fourth power. Or this is, well, x to the fourth is the thing that we're taking to the fourth power and then the fourth root of that. And we see that because we're taking an even power and an even root, we should put absolute values around here. Now, this technically is not wrong. This is technically a correct answer, but it's not the simplest answer. Why is that? Well, note that x to the fourth, or x, a real number, well, x to the fourth, if I put a negative number in, gives a positive number out. Positive number in gives positive number out. 0 in gives 0 out. X to the fourth is already bigger than or equal to 0. Do I need the absolute values here? I don't need the absolute values here because x to the fourth power is already always non-negative. If I want to write this in simplest form, I can get rid of the absolute values. So it's not that I just didn't write the absolute values because I forgot to. They were important up here. Why is that? Well, if I take a negative number cubed, that gives me a negative number out, and I better have those absolute values there to make it positive. But here I had my absolute values. I put them on like I'm supposed to when I take an even root of an even power. So I did that. But then I asked myself, just like if I had gotten, a couple of numbers out of here, if I had gotten 2 times 3 or something, I would write that as 6 to simplify it before I write my final answer. I ask myself, okay, absolute value of x to the fourth, is there any way that I could simplify this? And I do notice that, say, an x to the fourth, or an x squared, or an x to the sixth, x to an even power is already always non-negative for a real number input. So I have no need for the absolute values here. The simplest form is going to be to just take the absolute values away because they're not needed. So I put them in from the process of taking the root, and then I got rid of them because in this case, they're not needed. Here, I put them in from the process of taking the root, and then I kept them because I can get negative outputs of x cubed, say by, putting in, say, -1 or -2. So I better have those absolute values there to make sure that if I put a negative input in, I get a negative output out of x cubed, and then the absolute value switch it to make sure that it's a positive number. Because of course, if I put a negative input into the original expression, it's going to get raised to the 12th power. That negative gets squared off, so to speak. And then when I take the fourth root, I end up with a positive number. So this is positive or 0, I suppose, as is this. But if I didn't have those absolute values, on the left side, I'd be saying that I always get a positive output. On the right side, I'd be saying sometimes you get a positive, sometimes a negative output. That clearly wouldn't be correct. So I'm trying really hard to make it not seem like I'm saying, you know, don't put absolute values in, don't put them in, put them in, don't put them in, like randomly, right? I'm trying to make it very clear what we're doing here. We follow this rule all the time. So we always follow this rule. We did it here, we did it here, we did it here, we did it here, and we did it here. We followed that rule. I followed that rule every time. But it just so happens that I can simplify this after I apply that rule to get rid of the absolute values. I didn't ignore the rule for some reason. I followed the rule. I looked at my expression and said, oh, I can simplify this expression. I can get rid of the absolute values in this case and still have an equivalent expression that is a little simpler because it doesn't have the absolute value symbols. So I want to make very clear that I followed the rule in every one of these problems, but here I just happen to be able to simplify a little further and get rid of those absolute values. So I did have to kind of like put them in and then get rid of them. But that's okay. I'd rather do those two steps than try to come up with some really complicated rule with a bunch of if this is true, then that, I'd rather have a simple rule that I follow every time. And then I look for simplifications, right? That breaks it into two steps rather than have one really complex rule that's probably very difficult to follow. So my rule that I follow all the time is if I take an even root of an even power, I put absolute values in. If I take an odd root of an odd power, I do not put absolute values in. And then when I end up with something that might have absolute values in it, I check whether those absolute values are actually necessary. Is the thing I'm absolute valuing always a positive or zero? If so, then I can get rid of the absolute values and I'm fine. If the thing I'm absolute valuing has some instances where I could get a negative output, I'd better leave those absolute values there because they're actually doing something in that case. Okay, what about something like this? Negative square root of 16x to the fourth y to the sixth. Well, here I'm going to make use of a square root property that the square root of a times b, if a and b are bigger than or equal to 0, is square root of a times square root of b. Remember, these radicals kind of act like exponents, and we're going to see that very explicitly in the next section. These radicals kind of act like exponents. So it's kind of like I have two different bases raised to the same exponent, and I'm like distributing the exponent into the bases. That's essentially what's going on here. This is applying a right distributive property. But I can split up square root of a times b as root a times root b. Now, it is important to note that this is only in the case that a and b are positive, because, I mean, I want these to make sense, right? I don't want to say that square root of 4 is square root of -2 times -2 is like root -2 times root -2. Like, what do these mean? And this clearly means 2. And I don't know what these mean. So I don't want to do something like this. This is only when a and b are positive. But I do see that x to the fourth and y to the sixth are both positive numbers, or at least non-negative. I should say non-negative, not necessarily positive. So I can look at this as negative square root of 16, square root of x to the fourth, square root of y to the sixth. And I see that this is going to be negative. Square root of 16 is 4, or radical 16, the principal square root of 16 is 4. Square root of x to the fourth, this is the square root of x squared squared. So I get an x squared out. I took an even root of an even power. I put absolute values on it. Square root of y to the sixth is y cubed. And again, this is y cubed squared, square root of that. I took an even root of an even power. I put absolute values on it. And now I look to simplify. -4, you can't really do anything with that. Absolute value of x squared. Well, x squared, if I put negative or positive in for x squared, I get a positive out. If I put 0 into x squared, I get 0 out. I don't need these absolute values. Y cubed, if I put a negative in for y cubed is negative, I do need the absolute values there. So this answer would be something like -4x squared times the absolute value of y cubed. Note that this negative in front, because it's in front of the radical, just kind of comes along for the ride. Any questions so far? Okay, so back to working with just numbers. We're going to follow the lead of this example up here and try to simplify square roots that aren't, say, square roots of perfect squares, or cube roots that aren't cube roots of perfect cubes. So say like square root of 48. Now I can't write this as a number like 7 or something like that. I mean, it's almost 7, but not quite. It's not going to be a nice integer solution. 7 squared is 49, 6 squared is 36. So we know that the answer is going to be between 6 and 7. But I might be able to write this as a simpler form with a radical in it. So let me look at 48. And I know that 48 is, say, for instance, 6 times 8. 6 is 2 times 3. And 8, I'll just write that as 2 cubed. So 48 I could write as, what, 2 to the 4th times 3. Really what I kind of see up here is if I can write something on the inside as a perfect square, like 16 is 4 squared, I can kind of pull it out of the radical. And the act of pulling it out of the radical just strips that square away. So 4 squared inside the radical becomes a 4 outside the radical. Or x to the 4th, x squared inside the radical becomes x squared outside the radical. 2 to the 4th, 2 squared inside the radical becomes a 2 squared outside the radical. Now this 3 doesn't have kind of a twin factor, a second factor of 3 to match against it to make it like square root of 3 squared. It's kind of stuck in the radical. Right. So square root is almost like saying, you can only come through the gate if you like have a twin. And when you come through the gate, we like merge the two twins together into one entity. Or this would be 2 squared is 4 times the square root of 3. So we could write square root of 48 in a slightly simpler version. We didn't completely get rid of the square root, but we made the stuff under the square root a little bit simpler, a little easier to work with. Square root of 3 that we're dealing with instead of square root of 48. Or if we look at cube root of 96, so what's 96? It's going to be 4 times something, 4 times 24, or it's going to be 2 times 2, 6 times 4. So it's what? 2 squared times 2 times 3 times 2 squared, or it's 2 to the 5th times 3, I think. So 32 times 3 is 96. That does check out. So this is the cube root of 2 to the 5th times 3. So now I'm saying that I need triplets. I need 3 powers on the inside to pass through the cube root and become 1 power on the outside. right? Similar to kind of what we did up here, we had 3 factors of m cubed that passed through the cube root and became 1 factor of m cubed, for instance. So 2 cubed on the inside can come out as a 2 to the first on the outside. I used up 3 of the powers of 2 to do that. I have 2 powers of 2 left over to make a total of 5 powers of 2. And then times this 1 power of 3 that doesn't have any, siblings, so to speak, that's stuck in there. Or this would be 2 times the cube root of 4 times 3 is 12. So 2 times cube root of 12, that's as simple as we can make this one. Cube root of 96. Any questions so far? Now, where can this be helpful? Maybe in something like this, where I want to simplify, say, 12 minus square root of 18 all over 3. Well, one thing I can do right away, I see, is split this into 2 fractions. And 12 over 3, of course, is just 4. But what is the square root of 18? Well, I can rewrite 18 as 9 times 2, or I recognize that 9 is 3 squared times 2. I have the square root of 3 squared times 2. That factor of 3 squared can come out. The square root kind of strips that power 2 off, and we get 3 times square root of 2. Now, don't get too worried that there's a square root of 2 here. This would be like if I had 3x over 3. Oh, I copied it down wrong. I think I was saying square root of 2 and meant to write that denominator of 3. This would be like if I had 3x over 3 or 3 times 4 over 3. We can divide out the 3's. If I have 3 times square root of 2 over 3, I can divide out the 3's just like anything else. It's just 3 multiplied by something divided by 3. These divide out. So I could simplify this all the way down to 4 minus square root of 2. Any questions on any of this? Okay, what if I have the cube root? This this sometimes shows up a little bit strangely in Microsoft's equation editor, like to put the cube in the radical kind of all the way up there. But this is the cube root of 128 over 54. I guess I could maybe like split this into cube root of 128 over cube root of 54 and start simplifying. But before I do that, because the roots are a little harder to work with, let me try to start by simplifying the fraction 128 over 54. Well, 54, I think, is 9 times 6. And 128, I recognize that as, I think, a power of 2, right? 64 times 2 is 128. So 2, 4, 8, 16, 32, 64, 128. I think that's 2 to the 7th. Or I can divide out one of those factors of 2 and get 2 to the 6th over 9 times 3. Or that's 2 to the 6th over 3 cubed. So working with my fraction a little bit first, I'm now looking to do the cube root of 2 to the 6th over 3 cubed. Or I see that's going to be 2 squared cubed. That comes out as a 2 squared over 3 cubed comes through the cube root as just a 3. Or this is 4/3. That's my answer. Any questions so far? And now let's look at one of these problems with variables. So here we have the fourth root, note the 4 up there, the fourth root of 81, x to the 12th divided by x to the 5th. So I noticed that 81 x to the 12th over x to the 5th, well, 81 is 3 to the 4th power. X to the 12th over x to the 5th is x to the 12 minus 7, 12 minus 5, or x to the 7th. So this is the same thing as the fourth root of 3 to the 4th, x to the 7th. I probably ought to be a little careful here because I noticed that I started with an x to the 5th in the bottom, but I kind of divided it out. So I probably ought to say x cannot be 0. And now I'm good for the rest of the problem. I've taken care of that restricted value. Remembering back to rational expressions where I have things like restricted values that I might want to write out explicitly before doing any simplification. 3 to the 4th comes out of the fourth root as just a 3. And x to the 7th is x to the 4th times x to the 3rd. Right? Same base raised to powers. We add the powers together. So the x to the 4th factor can come out of the fourth root as an x. And hey, wait, I took an even root of an even power. I had better throw an absolute value on there. And then I have 3 factors of x left inside the fourth root. That doesn't have enough factors to make it out of the fourth root. It would need 4 or more. Not enough. So we have the fourth root of x cubed. That's left over. I definitely need this absolute value there. If I plug in x as a negative number, absolute x is going to be positive, so I need that absolute value to stick around. I can't do anything else with the fourth root. I don't have the only factors I have inside are x's, and I don't have enough factors of x to bring any more out. I think that's about as simple as I can get. Of course, with the domain restriction, x cannot be 0 coming from the original expression. There's nothing in this simplified expression that would naturally preclude x from being 0, but because we had some factors of x in the bottom up here, we want to make sure that domain restriction pervades through to the end there. Any questions on this? Okay, then moving on to 8.3, simplifying rational exponents. So definition, if n is bigger than or equal to 2, then we say that a to the 1 over n power equals the nth root of a. So the nth root of a is a to the 1 over n power. Where does this notation come from? Well, remember that I got my n and m. I wanted to my n and m before. My n meant something a little bit different. So we'll switch to something like this. The nth root of a equals b says that a equals b to the n. But if I think of raising both sides to a certain power, what power could I raise both sides to get b by itself again? Well, if I have the nth power on b, I want to raise it to a power, something, so that n times that number gives me 1, gives me b to the first power, right? Well, naturally, that should be something like 1 over n. So I want to raise the other side to that power as well. b to the nth to the 1 over nth is b to the power n times 1 over n. B to the n over n is just b to the first, or b. So we kind of see that it is sensible to say that the nth root of a, we say, is the 1 over nth power of a. So strictly speaking, this is a definition, but it's a sensible definition because it's kind of consistent with what we'd expect from our power to a power property and so on. So we could write, say, for instance, x to the 1/3 as a radical expression, the cube root of x. We could write y to the 4/5. We recognize that y to the 4/5 is y to the 1/5 to the 4th power, because 4/5 is 4 times 1/5. Or I could write it as y to the 4th to the 1/5 power. When I have these rational exponents, there is a little bit of ambiguity here. And that's something maybe we'll leave to a future class, future class meeting, future discussion. But I'd probably write this as y to the 4th to the 1/5 power means take the 5th root of that. So the 5th root of y to the 4th. Or if I wanted to take the square root of 3x cubed, that's 3x cubed. The square root means raised to the 1/2 power. My power to a power rule, that is 3x to the 3/2 power. So we're not doing a whole lot of mathematical operations here. We're just getting used to this notation. And last one in this little subsection, 2y squared, the cube root of all of that. We could write this as 2y squared to the 1/3 power. Or I could, maybe if I chose to write this as 2 to the 1/3 power, y to the 2/3 power, that might be a preferable way for whatever I want to do next. Either of these would be a reasonable answer here. Okay, let me end the recording.